This is AP Calculus BC, and in this video, I'm going to talk about section 10.1, parametric equations, tangent lines, and arc length. So in this section, there's a lot of review material, but there's also a lot of material where we're going to start doing some calculus with parametric equations. And parametric equations are things that we use to allow us to introduce another variable into our system. So for example, these are typically used in a lot of cases where we're talking about motion problems or when we start dealing with vectors. When we talk about motion problems, we're usually talking about things changing with respect to time. Well, the way that we've been writing our equations up until now, we have y in terms of x typically. Well, what we can do with a parametric set of equations is we can have y as a function of time and x as a function of time. And what that allows me to do is it allows me to figure out things about what's happening with the x independent from the y and what's happening with the y independent from the x. So it allows me to get a lot more information about what's happening in my particular motion problem. So with parametric equations, these are things that you covered in pre-calc. So the basics of this, I'm not going to spend a lot of time on. I'm going to assume that you kind of know this, and this is just a brief overview. For the most part, we're going to focus on the calculus that we're going to use with some of the parametric equations. So just a really quick review here. I do have a set of parametric equations here that have been graphed, and I just want to remind you of a few things. So notice with my set of parametric equations, I have x is equal to t squared minus 2t. I have y is equal to t plus 1. And I've got the graph down below, and notice my table of points here. So in order to find an xy coordinate, I have to have a corresponding t value. So the t values are given in the first column, and then I've got the corresponding x and the corresponding y. Now, notice there are negative t values. We can have negative t values, so that's one thing to remember. A lot of times t is going to represent time. So in a lot of cases, our time will start at 0 and go forward from there, but we can also have negative t values. The parameter, even a negative t makes sense if we are just setting our 0 time to be some point. Anything that happened before that would be considered negative time. Anything that happens after would be positive. But the parameter is not always t either. I mean, excuse me, not always time either. Sometimes that parameter represents other things. So from the standpoint of how is this useful? Well, take a look at my graph. Not only am I getting the points on my graph that create this parabolic shape, but I'm also seeing which direction this object is moving as it goes through these points. And there's even more information than that. Look at the distance between the points. So the distance between the points is also telling me how fast this thing is moving. So since I'm going on a consistent time interval here, you can see that if I'm moving a longer distance over that time interval, I know my object is moving faster. So that's another thing that you can consider. It's not just the parabolic shape. It's the direction that I move through that parabolic shape. It's the distance between the points. A lot of things become apparent about the motion of our object when we graph these things. Now, a lot of times when we graph these, we are going to use the arrows because they indicate the direction. You don't always have the arrows in your graphs, but in a lot of cases, you're going to. Okay, so let's first talk about going back and forth between parametric form and just the standard rectangular form. So this is called eliminating the parameter. And what we're doing here is we're just saying, okay, we have x in terms of t and y in terms of t. What if we just want x in terms of y or y in terms of x? Well, what I've done here is I just said, okay, from the second equation, I can see that t is equal to y minus 1. So I solved that equation for t. And then I took that t and I plugged it into the first equation. Well, if t is y minus 1, that means x is y minus 1 squared minus 2 times y minus 1. And now I have x in terms of y. Okay, so it's fairly easy to do in a situation like that where you just have polynomial expressions. You can just isolate your t in one of the expressions and then substitute it into the other equation. Sometimes it's going to be a little trickier. Let's talk about graphing these things. So for these, eliminating the parameter is going to be a little harder, but we have two graphs that are actually pretty similar here. We have x is cosine t and y is sine t on the interval 0 to 2 pi. So I want to show you this on the calculator just as a reminder. And on the calculator, the first thing that you're going to want to do is you're going to want to change the mode on your calculator. So if you hit the mode button, which is next to the second button, and scroll down here to the fifth line, you can see that this is where I set the mode in terms of function, parametric, polar, and this is called sequential. We're not going to use that, but we'll use the parametric mode right now. So I hit enter. Once I have that selected, now when I go to my y equals screen, it's going to show sets of parametric equations. So my parametric equations here, x was cosine t. And notice that when I hit this x button, now that I'm in parametric mode, the x button is now automatically defaulting to the t. And then my y was the sine of t. Okay, so I've got both of those entered, and I want to use the interval 0 to 2 pi. So when I look at my window now, this has changed as well. Notice my t minimum and t max. So those are the t values that I'm going to use. In this case, we'll just say t is time. We're going to use the time values. So the t minimum, t max are already set. This t step is essentially telling the calculator how far am I going to go from point to point to create that table of points and then connect them together. So for my x values here, I'm just going to go from -2 to 2 on both the x and the y. Okay, so now when I graph it, I'm going to do one other thing. I'm going to go to the left of this where it highlights the color and what type of a line I have, and I'm going to hit enter. So I'm going to go over here where it says line. I hit the down arrow, and I'm going to change this by hitting the right arrow. And what I want to do is I want to select this one that kind of looks like an open circle or a ball and then a line. So what that's going to do is it's going to look like an object moving. So it's like a ball moving, and it's going to leave a trace behind where it's moved. So I'm going to hit OK on that. Scroll down here to OK. And now when I graph it, we'll see what happens here. So right now this looks kind of like an ellipse. I'm going to do zoom square, zoom, and then 5. And now you can see this is actually a circle. Now notice that it started over here at the point 1, 0, and it went counterclockwise about the origin. So it's not just the fact that I have a circle. It also has to do with the fact that where did it start? What direction is it moving? So some things that I can do, if that thing's moving too fast for you, what you can do is you can make your t-step smaller. Like I can make my t-step, let's say 0.01. Now it's going to move much slower because the calculator is actually plotting a bunch of points here. And I've just essentially multiplied the number of points by about 10. And now you can see it moves a lot slower than it was before. It's still going to give me the same trace, but now it's a lot easier for me to see, okay, this is moving counterclockwise about the origin. Okay, so I don't want to go that slow, but you can definitely slow it down if you'd like to. Okay, so I'm going to change this back to be approximately 0.1. Okay, so going back to what we were looking at with the notes here. So it said to graph this, and then it said eliminate the parameter. Well, notice we had a circle centered at the origin, and it had a radius of 1 when we looked at the graph. So the way we can eliminate the parameter in a situation like this is just a little bit different. And the way I'm going to do it is if I were to think about x squared plus y squared in this case, that would give me cosine squared t plus sine squared t. Well, what's cosine squared plus sine squared? That's actually equal to 1. So what I end up with there is x squared plus y squared is equal to 1. So now I've got a circle with a center at 0, 0 with a radius of 1. Now, I lost some information when I did that because now I don't know where this object started. I don't know which direction it's moving. But I do know I have a circle centered at the origin with a radius of 1. Okay, so let's look at another one that looks very similar, but it's slightly different. So we have x is sine 2t, y is cosine 2t on the interval 0 to 2 pi. Okay, so I'm going to go back to my calculator, and I'm going to graph this. Okay, so on my calculator, we had x was equal to the sine of 2t and we had y was equal to the cosine of 2t. Now, when I graph this, let's take a look at what happens. Notice it started at the point 0, 1, and it actually completed 2 revolutions this time. So it still ended up with a circle, right? I've still got a circle centered at the origin with a radius of 1, but this is actually very different motion than we saw in the previous problem. If we just look at the end result, they're exactly the same, but the information from the parametric form is giving me a lot more about what's happening with this object. Okay, so I still have x squared plus y squared is equal to 1 if I eliminate the parameter. So let's eliminate the parameter on this one. And to do that, I can just do x squared plus y squared. That would be equal to sine squared 2t plus cosine squared 2t. And that's equal to 1, which means x squared plus y squared is equal to 1. So exact same equation, right? So if I only look at the end result, you would say, oh, these are exactly the same thing. There's no difference. But the reality is these are very different. What we have here on the first one, we had a situation where this started at the point 1, 0. And then as it rotated about the origin, it moved counterclockwise and it made 1 revolution about the origin. Okay, so yes, it was a circle, but it also started at 1, 0 and it moved counterclockwise. It made 1 revolution. Well, for the second one, this time it started at 0, 1. And this time it moves clockwise and it made 2 revolutions. So yes, they are similar graphs, but they're not the same from a motion perspective. They're very, very different because they have different starting point. They have different direction. The only thing that is similar from a motion perspective is that the path they follow makes the same shape, makes that same circular shape. Okay, so what I have on the next page here is an exploration that I'm going to have you try here in just a second to start to get a feel for how some of these things work from a calculus perspective. We're going to start analyzing the x and the y independent from one another. We're going to talk about an x rate of change. We're going to talk about a y rate of change, and we're going to look at that graphically. So before we do that, let's just talk about a couple of things here. When we are dealing with parametric equations, we can get a dx dt, and that's the rate of change of x with respect to time. We can get a dy dt, that's the rate of change of y with respect to time. And if we want to go from a dy dt, dx dt type of situation back to eliminating the parameter, well, we can do that pretty easily using some algebra. If I want dy dx, all I have to do is dy dt divided by dx dt, because if you flipped the dx dt and multiply, the dt's would cancel and you'll get dy dx. So you can always get the slope of the tangent line if you want to by dividing dy dt by dx dt, just thinking about that algebra. So as you go through this exploration, that's what I want you to try. So I want you to take a couple of minutes and I want you to try this problem. So you're given a set of parametric equations, and then they're going to kind of walk you through a lot of basic ideas of dealing with rates of change with parametric functions. So pause the video. When you come back, I'll go through the solutions for this. Okay, so here are the solutions that you should have ended up with. On the first question, for number 2, it says find dx dt and dy dt, or find equations for dx dt and dy dt, and then evaluate the 2 at time is equal to 6. So I took the derivative for the x equation with respect to time, and you can see my derivative, and then I plugged in 6, and I got 1.0546. So that's how x is changing with respect to time. It's moving in the positive direction at a rate of 1.0546. The y is changing in the positive direction at a rate of 3.6754. Okay, so number 3, they asked you to find dy dx. Well, dy dx I can get from dy dt and dx dt if I divide dy dt over dx dt, and I get about 3.4849. So that is still the tangent slope. If I were to graph that curve at time is equal to 6, that's the slope of the tangent line, 3.4849. All right, number 4, find the answer for dy dx numerically. So on your calculator, when you're dealing with these parametric equations, what you can do is you can hit second and trace, and this calculate menu has changed a little bit. I can actually find dx dt, dy dt, and I can also find dy dx. The calculator will find that for me. So that's what they were wanting you to do on that, was to actually use the calculator to evaluate dy dx. And you would see that we get the same value. But the main thing is that calculate menu has changed now that we're dealing with the calculator in parametric mode. All right, number 5 says Adam starts out at the origin and goes to the northeast for a while. At approximately what value of t does he turn back around and start coming back? So what I did here is I just graphed this on the calculator and traced along my graph. And I can find that it's roughly somewhere between time is 0.82 and 0.86. All right, number 6, it asks you to actually sketch the graph. And so all I did here was plug it into the calculator. I plotted the graph, and then this is just a rough sketch of what that looks like. Okay, number 7, find precisely by calculation the value of t at which y first stops increasing and starts decreasing. So even though we're now dealing with parametric functions, we're still dealing with the same basic calculus concepts, right? So my y value is going to be at a maximum at some point. Well, I'm going to set dy dt equal to 0. If y goes from increasing to decreasing, that's a maximum y value. So we set dy dt equal to 0, and that occurs at approximately the time 0.8229. Okay, number 8. At the time in problem 7, is Adam stopped or is he still moving? So what I'm doing is I'm taking the time from question number 7, and I'm saying, what's dx dt at that point in time? Well, dx dt is really small, but it's not 0. So he didn't actually stop. He just stopped moving in the y direction, but he's still moving in the x direction, very slightly positive in the x direction. So he's not actually stopped. So in order for you to have a complete stopping point when you're talking about motion in a parametric form, both dx dt and dy dt have to be 0 at the exact same moment in time. Okay, so even though it looked like when we first sketched this that there might be a cusp in the graph, if you zoom in on that point enough on your graph, you'll see there's not actually a cusp in the graph. There's a slight curve there because we're not coming to a point where we're instantaneously changing direction like it may have appeared. All right, so let's go back over to talk a little bit more about some of this calculus. So we talked about finding the slope of the tangent. Now, when we're talking about these parametric curves and we're talking about a horizontal tangent line, horizontal tangent line still means the same thing. It means we have a slope of 0. So if you want to reason through this, you're always thinking about this relationship. In order for us to have a dy dx value of 0, the numerator needs to be 0 when the denominator is not, because that would give us a 0 divided by a non-zero number is going to be equal to 0. If we want to have a vertical tangent line, that means dx dt, the denominator is 0 when the numerator is not. Okay, and then if they're both 0, that's typically where we're going to have a cusp in our graph. Like we just talked about on that previous problem, if both dx dt and dy dt had both been 0 at the same time, we would have had a cusp, but they weren't. So that was how we were able to identify there wasn't a cusp. Now, where this gets tricky is when you start dealing with second derivatives. When you're looking for second derivatives, and we're talking about concavity again, second derivatives are a little tricky because we have to understand some differential calculus here. So what we're doing is we're trying to find dy dx. Well, to get the second derivative of y with respect to x. So what we're doing is we're taking our dy dx and we're taking the derivative of that with respect to time. So remember, our dy dx was dy dt over dx dt. So we're going to take the derivative of dy dt over dx dt with respect to time, and then we're going to divide by dx dt. And if you notice what happens here, when I flip and multiply, what I have here is the dt's canceling out, and I end up with d dx of dy dx. Okay, so the reason we have the d dt there is because our dy dx is going to be in terms of time. So we take the derivative of that with respect to time and we divide by our dx dt, and that's going to give us our second derivative of y with respect to x. That's the one thing when we're dealing with parametric calculus, this is the one thing that tends to throw people just a little bit. But remember, this expression for us is typically going to be in terms of t. So we can't really take the derivative of dy dx with respect to x. We have to do it with respect to t first and then divide by dx dt. And notice here, we can't just do the second derivative of y with respect to t divided by the second derivative of x with respect to t. That doesn't give us our second derivative that represents concavity. Okay, so let's just take a look at one problem here where we're going to go through some of these basic calculus ideas. So we have a set of parametric equations here. We have x is t squared and we have y is t cubed minus 3t. So when I go through this, I'm just going to go through the basic ideas. I'm not going to go through a bunch of the individual steps, but I want to show you the main calculus steps you have to think about. So it says, first thing we want to find is the equation of the line tangent to the curve when time is equal to 3. So if we want a tangent line, still go back to the stuff we did at the very beginning of the year. If we want a tangent line, we have to know a point and a slope. Well, for our point, we need to know what's x when time is 3. Well, that's equal to 9. What's y when time is 3? And I'm just looking at these parametric equations. That's equal to 18. The other thing I need to know is what is my slope? Well, dy dx is going to be dy dt divided by dx dt. Dy dt would be 3t squared minus 3. I'm just taking the derivative of that y equation. Dx dt would be 2t. I'm taking the derivative of the corresponding x equation. And now I can evaluate what's dy dx when time is equal to 3. And that would be equal to 4. So in the end, I've got my slope and my point. My tangent line would just be y minus 18 is equal to 4 times x minus 9. Okay, so I have to do a little bit more work if I want to go back and do some of these sort of traditional calculus operations, but it's still the exact same thing, just represented in a slightly different way. Okay, so find points where the tangent line is horizontal or vertical. So remember, this has to do with where dy dt and or dx dt are 0. So for horizontal, first thing I have to think about is that means the numerator of my dy dx needs to be 0. Well, dy dt was equal to 3t squared minus 3. If I set that equal to 0, I get time is plus or minus 1. Okay, now I can't necessarily assume that that's going to be all of my horizontal tangents yet, because it's possible that dx dt is also 0 there. So I've got to check for my vertical tangents. Remember, for those, we need the denominator to be 0 when the numerator is not. Well, dx dt is just 2t. When I set that equal to 0, we can see that happens at time is equal to 0. So there's not a point where they're both 0 at the same time. So I don't have to worry about any cusp points. So for my horizontal lines, or at least the horizontal points of tangency, it's going to occur at t is equal to 1. Well, or t is equal to negative 1. So now I have to go back and look at my original equations. When t is equal to 1, my x is 1. And all I'm doing is plugging in t equals 1 into this. And then I can get the corresponding y. That would give me a y value of negative 2. So I have the point 1, negative 2. And then I can also plug in t is negative 1. And I get the point 1, 2. So those are my horizontal points of tangency. Okay, so now let's do the same thing for the vertical. When t is equal to 0, I get the point 0, 0. Okay, so again, things that we could have found before, we're finding in a slightly different way. Now, concavity, it says intervals of concave up and concave down. So we're still analyzing a function, or doing the same things as when we were analyzing functions before, but now we have this parametric setup. So I want y double prime, right? Well, that means I need second derivative of y with respect to x, and that would be the derivative of dy dx. So the derivative, my dy dx, we found up above in part A, it was 3t squared minus 3 over 2t. So I'd have to take the derivative of that with respect to time and then divide by dx dt, which is 2t. And when you go through and simplify everything down, what you end up with is 3t squared plus 3 over 4t cubed. Okay, so the only potential point of inflection that I have here, I want to set the second derivative equal to 0. Where's the second derivative? 0 or undefined. The only value I get here is t is equal to 0. And if I do a sign chart here for my y double prime around 0, you would see that it's negative and then positive. So that means we're concave down and then concave up on the interval. So for the concavity, I would be concave down on the interval negative infinity to 0, and then concave up from 0 to infinity. Okay, so again, same stuff we were doing back in the first semester with derivatives. It's just a little more complex now because we have to sort of work around the fact that we're dealing with these parametric equations. Okay, D, it says, what happens at the point 3, 0? Well, let's look at that. So at the point 3, 0, we have x is equal to t squared, right? So if I plug in 3 for x, I get t is equal to plus or minus the square root of 3. For the y value, I have t cubed minus 3t. If I plug 0 into that, I'm going to get 3 cubed minus 3t equal to 0, and I get time is equal to 0 plus or minus the square root of 3. Now, notice we have an extra point in time here where the y value hits the point 3, 0, or excuse me, the y value hits 0, and the x value is not at 0. But we have 2 points in time where we actually hit the point 3, 0 at the exact same moment. So what does that mean on my graph? It means my graph is somehow intersecting itself. So let's take a look at this graphically. So I've got this set of parametric equations, t squared. And then for the second set, we had t cubed minus 3t. Okay, and I'm just going to graph this. Let's see, we've got some negative time intervals. So I'm going to go from -5 to 5. And I'll leave my t-step at 0.1. And when I graph it, here's what you see. Notice that 0.30, I crossed that value twice because that graph actually intersected itself. Now, when we were dealing with functions, it was impossible for us to get a curve like this that intersected itself. But now that we're dealing with these parametric equations, we're going to start seeing things that we weren't seeing before. Okay, so you do have a lot of problems on your assignment where you're just going to go through and analyze these parametric functions using the methods we were using before, but obviously it's slightly altered because we have to do a little bit of manipulation to get things, to allow us to get things where we have y into dy dx or d squared y dx squared. So it's just a little more difficult from that standpoint. All right, so two more things in here. We're going to look at arc length and surface area. And you might feel like this is a lot, but when you start working through these, you'll see this is actually fairly simple. Arc length of parametric curves. If you remember back to when we were doing arc length back at the end of the first semester, we had a derivation of that where to find the arc length, we were using just a bunch of small segments of a curve. We were treating them as line segments and then adding them together. Well, we're still going to look at this in the same way, but when we do this, there's actually an easier way that we can set this up. So this is how we looked at it before, right? We got everything where we had it in terms of dy dx, and we can solve it all out. Well, if we go back and look at this step right here, if I were to take this integral and say it's the integral from a to b of the square root of dx squared plus dy squared, and multiply that by dt over dt, what I can do is I can take this dt and move it into the square root, and it becomes a dt squared multiplied to both of those. And what we end up with is this form of arc length. So the nice thing about arc length in a parametric form is everything's in terms of t. So for my setup, it's just dx dt squared plus dy dt squared inside the radical. And then these limits of integration are just going to be time values now, or t values, parameter values. So fairly simple to do. We just need to know dx dt and dy dt. So even though it looks different than the arc length setup we had before, it's still the exact same derivation that we had. Okay, so let's just look at a couple of quick examples. Find the length of the curve defined by the following equations on the given interval. X is cosine t, y is sine t. So that's a circle on the interval 0 to 2 pi. So if I wanted to find the length of the curve, that's a circle with a radius of 1. I should be ending up with 2 pi because I know the circumference is 2 pi r. But let's look at this from an arc length perspective. So we would do the integral from 0 to 2 pi, square root, dx dt is negative sine. We'd square that. dy dt is cosine. We'd square that and then multiply by dt. Well, essentially what we have there is sine squared plus cosine squared is 1. So we just have 1 integrated over the interval from 0 to 2 pi, and we get a length of 2 pi. Okay, so very simple to do. Most of the time on these problems, we're going to plug them into the calculator. On that one, we didn't even need to because it simplified down so nicely. Let's look at one a little more complicated. Find the length of the asteroid defined by x is cosine cubed t, y is sine cubed t on the interval 0 to 2 pi. All right, so let's just set this up. For our length, we know we're going to integrate on this interval 0 to 2 pi. And then I'm going to have the square root. My derivatives are a little messier this time. dx dt is 3 cosine squared t times negative sine t. And then I'm going to square that. Plus, for the sine piece of this, I'm going to have 3 sine squared t cosine t. And I'm going to square that. And all of that times dt. And if you plug that into the calculator, if we really wanted to, we could play around and do things with trig identities and solve this out. That's not really what I want you to do. I want you to just plug this into the calculator. When you plug it in, you would see that your length actually turns out to be exactly 6. Okay, so even though it seems really complicated because we have this more difficult looking graph, it's not a function. We're dealing with things we haven't dealt with before. It still boils down to the same calculus principles that we've been dealing with for the entire year. All right, last thing I want to talk about here is surface area. Remember, surface area is very closely related to arc length. So we talked about this at the end of the first semester as well. When we think about surface area, we're thinking about thin bands of area being added together. Those bands of area are closely related to arc length because essentially what we're doing is we're taking this little length and we're revolving it around our axis to create that band of area. So remember the arc length setup that, or excuse me, the surface area setup that we had in the first semester had all of this stuff in there, which was essentially the arc length. Well, now that we're doing this from a parametric perspective, you can see how all we have to do is essentially substitute in and get everything in terms of, you know, t instead of in terms of x and y. So depending on which way we're going to revolve, our radius could be the y or the x, but the main thing is we're just integrating over some time interval. So we just have to make sure we're measuring our radius in the correct direction. Okay, so let's take a look at an example. Find the area of the surface obtained by rotating the given curve about the x-axis. So since I'm revolving about the x-axis, that means the y is going to be my radius. So for my surface area, remember it's 2 pi r. So 2 pi is going to be outside the integral, so I can get my exact solution. My radius here would be t squared. That's how far away from the x-axis I am at any particular moment. And then dx dt is 3t squared. I'm going to square that. dy dt is 2t. I'm going to square that and then multiply by dt. And then again, just like before, we're going to plug that into the calculator and get your solution from there. So for the most part, we're doing a lot of the same stuff that we were doing back in the first semester, but it's going to feel different when you first start working through these, just because you're having to work in a parametric form as opposed to working in, you know, just the standard rectangular form. Now, keep in mind, the main reason we're doing all of this stuff with parametric equations is because this is actually leading us into vector calculus. So vector calculus, for I think everybody in here has worked with vectors at least a little bit. Remember, with vectors, we typically think about components of the vector, right? We have like a horizontal component and a vertical component. That's essentially what our parametric equations are. The x component is like our horizontal component, and then the y component is like our vertical component. So keep in mind, as you're working through this, we're heading towards vector calculus. This is sort of a transition to get there.